Here's a solution to an example of an optimization problem from the online homework. When we read a problem like this, we should immediately focus on the optimization word in the problem. In this case, the word is minimize, and then we want to see what noun that modifies, and we're trying to minimize cost. So we see cost here, so that means that we want a function whose outputs are cost. So we want to figure out cost equals something. Ultimately, our goal is for that to be a function in one variable, but one thing at a time. Let's first figure out if we can see what the cost will be in any terms, and then see what we need to do. So they've done us a favor by drawing the picture already, so that's nice. If they didn't, we would want to try to draw it and decide on what variables to use to describe the dimensions. The fact that the box has a square base is why they decided to label both dimensions of the base by x, and then the height could be anything, so the height is y. And so if we just go piece by piece in the problem, you'll see that the material for the top and the material for the bottom are different. They have a different cost. They're made of something different, probably thicker cardboard, and then the sides are made out of something much thinner, which is a lot cheaper. And so, so the cost of the box will just be the number of square feet that we use in each of the top, bottom, and sides times the cost of the material for the top, bottom, and sides. So, so it's a fairly straightforward thing to do. We just have to make sure we account for everything. So, so let's start with the bottom. The bottom of the box cost 20 cents per square foot. That's what it says here in the problem. And the dimensions of the bottom are x by x. So x by x would be x squared. That's how many square feet are in the bottom of the box. And each square foot costs 20 cents. So I'll just use 20. I won't use 0.20. We'll keep the numbers simpler. Since all the costs here are given in cents, our cost function will just be in terms of cents instead of dollars. Let's add to that, what does it describe next? The top material is 15 cents per square foot, so the top is also x by x, and so there are also x squared square feet in the top of the box. That's this part up here. It's x times x is the number of square feet in the top, and each square foot costs 15 cents, and so 15 cents times the number of square feet will be the cost of the top of the box. The sides all have dimension x times y. So that's how many square feet are in the side of the box. Every square foot of the side material costs 1.5 cents, so we did get a little decimal going on in there. After all, 1.5 cents per square foot. But there are 4 of those, so each of the 4 sides will have that cost, and so we could just multiply it by 4. Or you could just add it 4 times, whatever you want to do. But it should feel like we have decided the cost of each of the 6 sides of the box. We have the bottom of the box, the top of the box, and the 4 sides of the box. So the only thing wrong with this as a cost function is that it uses an x and a y. It uses 2 variables. And we will talk about how to deal with 2 variables soon in our course. But in this unit, we want to go through the extra effort to make this a function of 1 variable, which in this case we can, because we are also told that it's not just any box. It's a box that has a volume of 1,024 cubic feet. And so what that tells us, we can put over here, is that 1,024 is the volume, but the volume of a box is just the product of its 3 dimensions, so x times y. So x squared times y has to be 1,024. That has to happen. We have to have some relationship between x and y if we're going to be able to eliminate one of these variables. And the way we eliminate a variable is we just take the equation that relates the 2 variables and we solve it for one of them, and we substitute into the equation to get rid of it. So in this case, if I want to get rid of the y, I want to solve this equation for y and substitute, and that'll do it. So let's take that extra step. I'll go ahead and simplify the 20x squared plus the 15x squared. There's no reason for that to be 2 separate things. And I might as well go ahead and simplify the fact that I know that 4 times 1.5 is 6. And so now I can say, well, instead of y, so I have 4 times 1.5 is 6, the x is still x. Instead of y, I want to write what y is equal to. Well, according to this equation, y is equal to 1,024 over x squared. In other words, what I've done here is just solve this for y by dividing both sides by x squared. So if I divide both sides of that equation by x squared, it says y equals 1,024 over x squared. And so that's what I'm substituting into this equation to get this thing. And now this really is a cost function that just has one variable in it. So it's okay to call that c of x. And I can do one more simplification, which I might as well do, because the simpler it is before I take the derivative, the easier it'll be. I have an x here and an x squared here, so this x is going to cancel with one of those x's. And I also have 6 times 1,044, which I could do. That's 6,144. So let me just write that down. So I'll have 6,144 divided by x. So that is the cost function. We know that in order to find a maximum or minimum value, that we need to first locate the critical points. And so I'll go ahead and do that by finding the derivative, which will be 70x minus 6144 over x squared. And I'll solve where that's equal to 0. So 70x minus 6144x squared equals 0. That happens if I multiply through by x squared and then divide by 70, I'll eventually have x cubed is equal to 6144 over 70. And so x is going to be the cube root. That's not good. X is going to be the cubed root of whatever 6144 over 70 is. So at that point, it's time to drag out a calculator. And the cube root of 6144 over 70 looks like it is 4.444. So x is approximately 4.444. Remember that the x here is the dimensions, and we're measuring these things in feet, so the x units are feet, so feet. So this box, the box that is the cheapest box we can make that would hold this volume, would be 4.44 feet across the bottom 2 dimensions. Be square on the bottom with 4.44 feet. And then its height is going to be whatever the height has to be in order for the volume to be 1,024. In other words, I can go back to this relationship, and if x is 4.444, then the question is, what is y? And so that means we need to know what y is equal to in this formula, but that's what we did over here already. So this right here tells us that whatever the x is, the y is 1,024 over that squared. And so I can just divide 1,024 by 4.444 squared, and I'll get a y value of 51.85. Oops. And that's feet again. And so, well, first of all, this is a big-ass box. I mean, that's a giant box. So 4 feet on a side and 51 feet high. That's a little crazy for a box size. But we should have expected that, because 1,024 cubic feet is actually quite, that's quite large. That's like the size of a room. Anyway, so that's how we do it. If the question here is what are the dimensions, and so the answer is going to be that it's 4.44 by 4.44 by 51.85. Those are the dimensions. If it asks for the cost, don't forget that we can find that out by just plugging our 4.444 feet into the cost function into here. And it looks like that's about $21. So that's about how much it costs to make this big-ass box. If you're wondering about the endpoints here, this is one of the optimization problems where there are no natural endpoints. There's no, I mean, certainly x can't be negative, but x can really technically be as small as you want. It could be a 1/10 of an inch, and you could still draw a crazy looking box. That's a 1/10 of an inch on the base on each side, and then just super, super high. And so there's really no upper bound, and there's no strict lower bound other than that it can't be negative. And so when that happens, when we don't have the endpoints to check, we really should check. Technically, we should check to make sure that this value we're getting, this one critical value we're getting down here, really is a minimum, All we know that it's a critical value, but for all we know, it could be a maximum. But it's the only critical value, and there are no endpoints, and so that means that this critical value is going to be a maximum or a minimum for sure. If that's the only place the max or min could be, then that's where it is, if there is one. So the easiest way, I think what they do in the book, the easiest way to just make very sure that you really didn't answer the question wrong, in other words, that there really is a maximum here, is just to take the second derivative at x and verify, because second derivative here is 70 minus some giant number over x cubed. And if you check C prime at 4.44, you'll find out that that is positive. And so that means that, this is along the lines of the second derivative test, so that means that at this critical value, 4.44 feet, the graph is actually shaped like this. And so that means that at 4.44 feet, you really do have a minimum there. And because that's the only critical value, that has to be the absolute minimum.